Thank you. Good morning, everybody. My name is Annabelle Morisseau. I'm the Executive Director of the Smart Energy System Campus in France, in Grenoble. I am very pleased to welcome you for this first conference regarding the Erasmus Plus Green Tech project. Before we start, I would like to thank Eric Keppels from KBA for hosting us and organizing this event. Thank you very much, Eric. I think we expect about 50 people to attend this conference this morning, about 20 people here on site and people online. So thank you, everybody, for joining us and being there. Here is our program for this morning. I will start with a brief introduction of the project and I will present the team. You will then have a presentation of the stakeholder mapping done by Tenerdis and a presentation of the preliminary survey done by KBA. Next, we will take a little step aside and share the experience of another Erasmus project, which is going to be nice and very useful as we are just starting to build our training modules. After that, each training organization will explain the blueprint of the modules they are in charge of. And last but not least, we will dedicate 30 to 45 minutes to discuss with you, the audience on site and online. So if you have any question, please save them for the end of the conference. We will have time for that. Okay. So what is the purpose of the Green Tech project? First of all, as I hope you are all aware of, we share a worldwide challenge. We need to address the climate change and we need to achieve before 2050 zero carbon transition. To reach that goal, we need to be able to manage a more complex energy system. And so we need to acquire and to teach new knowledge. So this is why it is important to train more versatile technicians and to give them a whole picture of this complex energy system. But unfortunately, on the contrary, the observation, the analysis is that we lack in Europe, we lack qualified manpower and we lack especially maintenance technicians. In that context, the objective of our team through the Green Tech project is to break down the barriers between all individual energy system training courses to build bridges between the different energy system courses and create training module for technicians dealing with the new energy mix. So now here is our team to achieve this objective and this project. So we have Eric from KBA, who is hosting us today. Thank you, Eric, and who is in charge of the survey. We have Peter van Hout from UCLL in Belgium, who is in charge of the module dealing with network management and storage. Gregorio Blanco from XABEC in Spain, in Valencia, who will take care of the introduction module and the wind energy module. We have the colleagues from Lithuania, Jovita Kayukonite, I hope I pronounce it right, and Remigius Kaliassas, who are in charge of the first module with solar energy. and a big French delegation, Cyril Picard from IUT1, who take care of renewable gas, H2, and the usage module. We have the campus smart energy system, so with myself and Michel Burel. We took care of the website, and we take care of the MOOC. Nadia Gontier from the GIP for administration purpose, and Philippe Chesel from Tenerdis, in charge of the network of the companies and the mapping of the stakeholders. So most of us are here right now and will present and answer your questions. So today we are very happy to present you the first results of the project, which are in the upstream phase. First of all, we have a website for the GreenTech project. This website is important because it will allow us to disseminate as widely as possible and for free all the results, and especially the training modules that are going to be built. It is a commitment in all Erasmus projects to spread the result as widely as possible and for free for everybody. Secondly, the second achievement is a stakeholder mapping done by Tenerdis, and which is still going to be improved as the project goes on. And last, the preliminary survey has been completed also. But what comes next? I would say, and no offense, Eric and Tenerdis, what comes next is the most important, of course, because the expected results are now the training modules. So we have 6 training modules. The first one will be a general introduction. The second one will focus on solar energy. The third one, M2, on wind energy. Module 3 will deal with network management and storage. The M4, the H2 green production. And module 5, the usage. And all this module will take in account the recycling aspects. And last, when we have all the module, we will extract what is the most important knowledge, and build a book for, once again, dissemination purpose, and so that people can use it as widely as possible. So now I will give the floor to Eric, and thank you. Enjoy the conference.
Yes, Annabelle was right. The mapping and the survey are only byproducts. The most important, of course, is the modules that we were going to develop. Why would we want to do mapping of stakeholders? Well, we wanted to do a survey that was important for us in the first stage. So we needed a list of companies. So why not make something beautiful out of it and make a map out of it? So there's more reasons than that, because in the future we might also use that database to send out all the results that we have and to make interconnections, whether it's in this project or in future projects. And it's also available for everyone to see, so everyone can see which companies have something to do with renewable energy. It's still a work in progress. You can see here why it's still a work in progress. I myself did something for the Netherlands. You can see a lot of dots. If you list all the companies, then you get a lot of dots, because it's not just the big energy providers, but also the little companies that install a solar panel, for example. Then you get a lot of dots, but you can filter this out. But we still have to make sure how to do this for every country, at least every country that is involved in this project. So that's something we're gonna still work on the next 2 years, because this project will last for another 2 years. It will be connected to the website. So if you go to the website, you will not find it yet, but it will be in due time. It's a byproduct. The other byproduct is the survey and interviews we did. I haven't introduced myself, I just noticed. My name is Eric Keppels. I'm from KBA Nijmegen, or KBA Nijmegen in Dutch. We are a research institute in the field of education and labor markets. And I'm a senior researcher. I work 15 years there now. You can look at our website for more information. It's a bit outdated, but it will also be updated this year. Why did we want to do a survey and interviews? Well, we believe when you create content for education, you have to have a strong link with the industrial actors. So that's why we wanted to ask, what kind of needs do you have? And also take into account, because that's one thing we realized during our first phase, that we're dealing with 5 countries, but everything we create, we want to disseminate to all possible EU countries. And there are big differences in educational systems and also in the way the labor market works. So we needed to get more information about that. And also, we also had some ideas about the content, the first ideas on the content of the 6 modules we want to create. And we wanted to ask people, what do you think of it? Is it usable? Is it suitable for different type of workers? Is it suitable for different levels of education? What are your thoughts? And give us some information, give us some feedback on that. And I'll present you the feedback right now. I think everybody was given the report. If not, you can send me an email and I will send it again. The report is out now. It will be on our website in a couple of weeks' time, probably. I'm a researcher, so I have to say something about a response. We did execute it in all 5 countries. We got a response of 122 companies and institutions who filled in the questionnaire. It's a quite various group of companies and institutions, both on the labor market and education. They all, of course, have to do with renewable energy. You can see here, it's not just the companies who install or maintain solar panels, heat pumps, etc., but also big energy providers, people who work in R&D or in advice, and also some government agencies. Next, we executed 44 interviews in all 5 countries. We ask about the priorities for the energy transition to work. Where do we need to focus on? Well, when we ask about the energy sources for the future, most said, well, there are a lot of techniques, and it's important to develop a lot of techniques, whether it's hydro, geothermal, biomass. It's all interesting. Nuclear is a bit dubious. It depends a bit on who you ask. But there's a lot of interesting stuff going on. But we have to act fast. We really need to act fast, and what we call the low-hanging fruit, we have to pick them first. So that's mainly solar and wind. That's already here, but we have to implement it more broadly, more widely, and more fastly. We asked about technical developments. What are the main objectives there? What do we need to do? What are the hurdles that we have? Storage is the one that came on top. We need storage, whether it's battery, hydrogen, or other techniques. That's one very important technique that we have to master better. The other one is interconnections, and that was exactly why we did this project, the interconnections between the different energy sectors. We got lots of other suggestions as well. It's not just about getting more energy, producing more energy. It's also about using less energy, a more sober use of energy. It's about circular economy, reusage, and it's also about producing locally, storing locally, using that, producing it, using it, and storing it locally, even in a household. And to get there, we need to raise awareness, and that's something that's very important, whether it's through education or, unfortunately, which is also how it works is bigger price differences between old and new energy, between the fossil fuels and renewable energy, is something that works really well, unfortunately. What is the most important challenge to overcome? We also asked in the survey. Well, there are all kinds of challenges, but what's most striking is that people mostly didn't say it's not necessarily financial, it's not necessarily technological, it's not necessarily behavioral, but it's mostly strategical, governmental. And so I thought, well, that means we can do it. If it's just something that needs to change by government, we can do it. But then all our respondents say, well, there's a little bit more to it. There are lots of hurdles left in execution. Even now that the war is going on in Ukraine, prices are going up. We know we have to do something. A lot of people and a lot of governments know that we have to do something, but there are still lots of hurdles left in execution with all kinds of procedures and permit granting, etc., etc. That's one big hurdle. The other big hurdle are labor challenges, as already said by Annabelle. It's not just shortage of technical staff, it's also need of proper training because the technologies are changing so fast. And what kind of skills and competence are needed? We ask this really broadly. It's mainly practical and theoretical, precisely because the technologies are changing so fast. So we need to know what the possibilities are between the different energy sectors, what kind of interconnections can be made, how we can profit from it, and how to apply it and interconnect it. We also got feedback on the modules. As I said, we presented the blueprint of all these modules. Is it suitable? Well, it depends on how deep the knowledge goes, of course, and who you ask. But yes, it is suitable if it is an introduction course, and that's what we're planning to do. So yes, then you can use it for all kinds of professionals and all levels of education. And is it useful in all EU countries? Yes, that can be the case, but you have to make small enough piece of learning outcomes so everyone can pick whatever is right. And that's what's called building blocks. And we'll get a next presentation from Pepijn about this solution. We also got other tips in our survey and interviews. And they said, be aware, if we have done our work and in 2 years we have some beautiful content in 6 modules, we're not there yet. There's a lot more to do after this, which is marketing. They have to know us, they have to know that this is here. It has to be built into an existing study program, or a module has to be made. Of course, translation, but we also need teachers to study, to give this program, and maybe even training facilities. And of course, which is also a big hurdle we know, is that companies will have to be willing to give their employees this training. So there's still a lot of hurdles, but we hope to do the first step here. And we also got a lot of other tips during our interviews, because we are not the only ones working on this issue. Lots of people are working on it, but nobody has a really good overview. We also don't have a good overview, but I tried in our report to make first list of the people that I met and the projects that I got to know, so you can find them in our report in paragraph 3.4. That's it for me. As I said, it's a byproduct, but I hope you still enjoy reading the report. And if you're ready, Pepijn, I would like to give you the floor. Yeah, it's here.
Mag ook deze worden?
Mag ook.
Okay.
Ja.
Well, good morning, everyone. My name is Pepijn van Willigenburg. I work for the The Hague University of Applied Sciences, which is conveniently located here in Delft at the Rotterdamse Weg. So if you're from the Netherlands, and you know it's quite confusing sometimes. I'm a frequent visitor here at Green Village. There's quite a few direct current power electronics related projects over here that I'm involved in one way or the other. As you know, for example, I'm Pauline as well. But I'm here to explain to you a bit of the struggles that we had in our Erasmus Plus project called DC2Res, which the UCLL colleagues also know of, because the UCLL was also a partner in that particular project. And it's in the end, it may be so that the solution or the approach that we have developed might be of interest for you to also apply it or use it or replicate it in some way in your project. This is a bit of the table of contents that I wanted to share with you, some personal introduction, some introduction on the project, the challenges that we encountered, and the conceptual and a bit more additional or in-depth information on that concept that we developed. As I said, my name is Pepijn van Willigenburg. For the past 10 years, I've been working in electrical engineering related projects, which is of interest because I'm not an electrical engineer by myself. I've studied management of technology at the Hague University of Applied Sciences. But since I have been working in the electrical engineering field, I do know a bit of it. And it's interesting to see that there are bits and pieces with people outside of the electrical engineering field, which is quite a lot. It's sometimes more difficult for the electrical engineers themselves to communicate with. My present role at the Hague University is that of a business development manager, and I'm developing, well, mostly national, but sometimes also international projects at the Hague University, which is mostly Netherlands, Dutch-funded project, but also occasionally international projects. Of this particular project, the DC2Res project, I was the initiator, and which was, well, the initiation stage was also supported by Professor Aniek Dexters from KU Leuven, which was the relationship to UCLL. At some stage, I was also fortunate to become, without any prior experience in European projects, assigned as the coordinator of the project, which is an interesting, so without any prior knowledge on international projects. A bit more on the DC2Res project. In Dutch, we have a sort of saying, when there's many frogs and you have to keep them in a box in a way that's difficult. We had 14 frogs in a way, 14 different partners in an EU-funded project, 7 partners from Europe and 7 universities and universities of applied sciences from South Africa, which is quite a lot. You may recognize that it was quite a lot. The title stands for DC3 Direct Current Technologies, Renewable Energy Education and Skills Development Program in South Africa. So it was originally thought of as a sort of a directional project from all the knowledge and research that we had here in Europe on power electronics, direct current distribution systems, to transfer that or to help transfer that part to South Africa. That was the original idea. As you can see, the main aim was to develop a sort of an educational program, similarly of a semester, maybe 2, that every university would be able to work with. I'm not sure whether you're familiar with the energy-related situation in South Africa, but it's deteriorating rapidly. At the moment, there's 10 to 12 hours of load shedding per day. So you are grid connected, but well, maybe 10 to 12 hours of that day, you do not have access to power. In that situation, and so also your renewables, if they are grid connected, they do not work unless you can disconnect them from the grid somewhere. So it's from an engineering perspective of interest, socioeconomically, it's a disaster. That's something you can understand. Well, the sub-objective, or most important one, at least for you, I think, was to develop, well, it's a semester. It contained both theoretical parts, but also practical or lab or skill development related parts. What we have done here in Europe, for example, so at KU Leuven, establishing of centers where you have strong collaboration between researchers, education. This is something that was really not in existence in South Africa. I can tell you a bit more on that later on, but the roles, particularly universities of applied sciences, is totally different here compared to in South Africa. And there as well, quite a lot of challenges. So as you can see at the bottom, approximately one semester, it should contain power electronics and energy or power energy related courses, so with reticulation or distribution at different voltage levels. But then it got more, well, complex in a way, because then you start comparing your partners. Well, we're all universities or universities of applied sciences. We were just thinking of developing materials for a bachelor level. And then you start comparing these bachelor's courses, and then you see that some of them were 6 semesters, some 7, some 8. But in the end, everyone obtained a bachelor's degree, which is already quite strange. So it's all in the field of electrical, but sometimes electronics engineering, which is different from different learning objectives. But it's, well, if you look at it from a slightly larger distance, then it should be all relatively the same. But it was not. That's important to understand. Additionally, in South Africa, so-called honors program, you may recognize it, but it's actually a sort of an in-between program between bachelor's and master's programs. Because in South Africa, the qualification framework has 10 layers, and then there's an additional layer between a bachelor's level and a master's level, for which you require this honors level to be able to make the transfer from bachelor's to master's. I think that's an important difference. If you look at the European qualification framework, then there's no such difference in the Netherlands, but practically there is, because if you want to continue from, for example, a bachelor's from the Hague University of Applied Sciences, you do need something of a full semester of additional work before you can start. Practically, it's more or less the same, but if you look at the qualification frameworks there, it makes it more difficult. And then when you discuss your courses, your curricula, and everybody says, well, but we do offer power electronics in our courses as well. And then it gets a bit more complex, because what is it and what everybody does? And what levels? What are the learning objectives? What are the labs? The practical work that you do? What skills are you trying to teach your students? In what year of your stream? Particularly if you have a 3-year bachelor. I think UCL, you have a 3-year bachelor's program, isn't it? Yes, Peter. Well, we're relatively close by, and if we work together with UCL on other projects, you have, for example, you have, I think, a 2nd-year power electronics subject. Well, what our students get in the 3rd year, because we have a 4-year bachelor's program, which is already different. So it's very difficult to really compare them, and you have a sort of a one-size-fits-all semester, and where do you use that particular content? And then what you will notice, and it's something that you might realize already, with so many different partners, you will see that not all the people that are experts in that subject. And so it's quite difficult for someone to teach a subject which is, well, not really your area of expertise. Maybe you're more of an embedded systems engineer instead of a power electronics engineer, but you have to teach it because in your university you might be the best suited colleague, or you have the most time available, and you have to teach it. But it will differ quite a lot if you are the expert or not. And so how can you ensure students if you do not master the subject in the same way as someone else might do? And then an extra obstacle for us was the student numbers in South Africa, and the staff ratio. We have here in the Netherlands and in Belgium as well, and I think you may recognize it. Sorry, if you have questions, please just interrupt me. If otherwise, I'll just keep talking and spilling. Do feel free to do that. But the student numbers there were approximately 10-fold higher per year. And so where we have very small numbers, there I think the total of students studying electrical engineering at our university is, well, over all the years, it's about 250. the largest university of applied sciences in South Africa, Tshwane University of Applied Sciences, located in Pretoria. They had 2,500 students studying electrical engineering in the bachelor's programs. So anything that we can do, maybe with lots of student staff interaction, small scale labs, is something that you totally cannot use over there because they just don't have the number of staff or the equipment to do that anyway. So this was additional complexity on how could you transfer knowledge and skills, which is quite complex as well. But nevertheless, we did start similarly as you had in your project with a needs analysis. Okay, people know what do you need. And you can't read it, but I can share it, I can distribute it. What we try to do is from all the power electronics courses and the electrical power engineering courses to describe the learning objectives, the topics and other things that were in these courses to see if at some stage we could compare them. This is where we stopped approximately. There was so much content in it, so many things to compare. And with all the things that I shared earlier already, there is so much that you do not know about the other institutions, how to compare the levels of what you do, to say, well, I have an interesting course and it's something that you could use. So this is something that we want to develop for all partners. Well, the prior learnings of students might be different. They might be shorter there. They do not have the same practical skills. Might be different. So how can you then come to a sort of a universal or a one-size-fits-all solution? Well, we thought that we couldn't. That's a bit of the answer already. And then our colleague from KU Leuven, Annick Dexters, she had an interesting, very interesting proposal. She'd call a notes concept. Proposed to all the partners is to develop sort of blocks of very small groups or a set of materials which you could stick together in a way, a sort of a modular approach to learning materials. It's important, as you can read here, a note is to be a subset of a course, for example, for a lab. And we said, well, we want to use these notes around 4 use cases that we developed so that you have some guidance to what these notes should be about. From an electrical engineering topic, we said, well, we start with solar home style systems, then to a DC house, so a household level, then to a neighborhood, and then medium voltage DC. In a way, so to have in each layer you have more power, more energy, more complexity. In a way, that was good. And then and this was approximately the idea that we had. So there's content for these specific use cases, and eventually we thought, well, there's content that is not only fitting to one particular use case, but important to all the use cases. For example, basic sets for power electronics, for example, maximum power point tracking, which is used. This is different applications, which should then be a sort of a general use case, or sort of basic knowledge that you require. And this is what we start working on. And then I'll share with you the presentation that Annick Dexters gave during one of our general meetings. It was in June 2018 when we were visiting in Aachen. So it was in Germany to discuss what it is. And this is sort of the problem statement that I've been sharing with you, explaining the difficulties that we encountered from the basic idea, sort of one-size-fits-all solution. It doesn't work that way. That we do need to deliver something. Maybe this is an approach that we could use. And when I had a discussion with Erik, together with Annick Dexters, we, from our project perspective, had a sort of the conclusion that you are experiencing similar difficulties. And this idea that we have might be of interest to you. It's the invitation, I think. And the inventory matrix, that's the spreadsheet that I showed to you earlier. That's this one. I can share it with you in detail to let you show what we actually tried to in depth get to some agreement or understanding of what everybody was teaching. Well, we thought that this is not the way forward. So then she said, well, I'll try to explain to you. It's an idea that she had for many years actually. What these notes, what it should be and how you could use them. And if you look at it from a slightly different angle, these notes are actually a dissemination tool or activity. So if you have done research, maybe in the PhD or in the master stage, you should be able to really summarize or answer with the knowledge that you've gained in that master year of the PhD stage. You should be able to reflect on the things that you've learned and to really summarize that in a brief, very dense article which answers one particular question, actually, if it can. And if you answer too many questions, then you should split it up in different notes. And then you have very small building blocks in a way. And then you can have knowledge-related notes, application-related notes, or implementation-related notes, because you have different types of projects. Project-based learning, for example, in your university, you have to, or the CDIO initiative, I'm not sure if you're familiar with that, the MIT Educational Engineering, the engineering approach and conceive, design, implement, and operate stages in the project. You have to learn quite a lot of these aspects. And this was her idea of how to get used to that. And you can say, well, it's a note for a basic or for a more advanced or for experts, and you can have different levels of complexity in these notes. And something that is useful for a bachelor's degree might not be of interest at all to somebody at a higher level. So this is the basic idea. And in the blue bar, there's maybe the most important part. These notes are raw and validated material. So it's not meant as notes for a lecture that you could use in a copy, but it's meant for the staff so that they have very condensed booklet thing that they can use so that they can develop their courses with it. Because I don't know what your learning objectives are, how much time you have to teach this to your students, and what your specialty is. I can only share with you what I think that you should teach your students from different levels of complexity anyway. And that's this basic system. And maybe for the colleague from ISO, I saw just for your back, we have discussions with what's the name of your colleague, Jan and Henry Lotens. And Jan was very enthusiastic about this idea, and you're actually applying something similar but on a smaller scale. This is, well, maybe for half an ECTS, and you're working on an even smaller level. Some states even did discuss the idea on making these very smaller blocks fit into this node structure in a way. But so maybe to think of it as Lego in a way, to really structure from smallest elements and bring that together. And if you know you have this sort of a validation of the basic blocks, the basic knowledge that is in them, then in the end, it should be able for the others, so for the staff that will be working with your materials, to get to also a validated or an accredited course in a way. And that's on the bottom line. For example, at UCLL, you developed an interesting set of notes around your PV trailer that you've made. Set up literally a trailer or a tow car, which has some PV panels in it. It's got storage, it's got controls in it, protection, sustainable generator, I thought as well. And it can balance or act independently. It can balance the grid as well, or small grids. And you've made several sets and said, this is what we've done. This is the way we teach and train our students. We've summarized the bits. Please feel free to use this in this particular project. And in the end, we ended up that for all the South African part in the project, we procured similar components so that they could replicate this trailer and use the educational materials from it. this again, the story about the use cases. This was just an idea to structure it or to focus it, because electrical engineering alone, or energy engineering, if you want to call it, it's such a broad field. There's so many topics, you need to focus it in a way. So at the moment, we are preparing a new proposal for the upcoming Erasmus Plus opening, which again will have some South African, but also partners, but also from Malawi and Mozambique, to really look at energy poverty area electrification. But also again using this concept of nodes, so that people on other places are able to reuse it to their benefits in a way. And then additionally, we said, well, if you have these nodes, how do you then get to a way where everybody is not only staff, but also students actually can have access to these learning materials? And then we ran into Mr. Virus Kariman. He was a former internationalization office manager here at TU Delft. He's developing a platform for academia to collaborate in, which is called Academia. And there we have actually uploaded most of the content too. The idea is the owners want some control of the content that they generated. So there's a sort of a platform where there's individual spaces around that is controlled by the owners, the authors of these materials. And then people want to have access, they ask entrance to the owner of the materials, and then they can communicate with them directly. Also, if you have questions, you can directly ask the expert, the owner of the materials. Maybe communicating directly with students of others is something that you might not want, but this is something that the owner of the materials can indicate. Versus then it might be of interest to also consider other universities. Then you have to go into the approval of the credits for other universities, and that's something that we haven't done. But ideally, if your course is accredited in your country, it's at least area. On this platform, there's also some additional information on the project, what we've done. There's an overview of all the content that we've developed. There's some, because when we were, well, slightly more than halfway the project, late 2019, COVID hit us, so we had all sorts of plans for physical meetings, interaction with municipalities in South Africa. We had to cancel everything. Couldn't happen anymore. And then we had some video lectures, interviews with experts explaining specific concepts or projects that we had, for example, on to apply it in electrical installations using DC or electronic protection, or examples of projects in the Netherlands and in Belgium. So there's lots of information there already. And again, as I said, there's a members only section, which is free for academics, but it's over his materials, which is of importance to everyone. So you don't want any third one to meddle with your the page or the work that you've worked very hard on. And this is something we're still with the European Commission or the evaluators of a project. On some hand, you need to offer all your materials for free, the licenses, but still you feel responsible, or you are responsible for the materials that you develop yourself. So you need to have some level of control, but you can't control everything. And I think with this, I have shared with you everything that I wanted to share on the experience that we had in our project. Maybe it will help you to come to an approach or a decision that will help you in your future path. And if you want some additional information on this concept, or to apply or to use it, then it's something maybe that's best used to do via UCLL, because you're already slightly familiar with it. And then you're in practically neighbors. She might be able to assist you further if you want to. Thank you for your attention.
I think we go to questions. Go to the next presentation. Thank you.
Hello, everyone. And for online listeners, hello too. So I'm Jovita Kazikonytė. I'm from Panevėžys University of Applied Sciences, and I am Erasmus Institutional Coordinator. And in this project, I'm project manager. My colleague Remigijus, he's the researcher in this project. And of course, he prepared all this material, which I will present. And our model is solar energy. And first of all, of course, you can see where in Europe we are, Lithuania, I think Netherlands know where we are, yes. Generally, when we are going to other countries to present our university, nobody knows where is Lithuania. We are very small, but we are very happy today to be with you together. And our model M1 is solar energy, and we are the leader of this model, and together with Spain, Belgium and France, we have prepared the pilot model about solar energy. We created a descriptive sheet of the model, and our outcomes in there is able to assess ways of promotion of renewable energy technologies, able to explain the design, efficiency, and economic justification on solar cells, able to explain particularities of electric power generation using solar photo elements, principles of their operation, as well as area of their use, able to explain principle operating of solar cells, their advantages and disadvantages depending on various conditions, able to assess technologies for preparation for hot water using solar collectors, able to explain technologies for heating of buildings using solar energy and possibilities for the use of them, able to assess critically the role of the circular economy in sustainable progress. Of course, the descriptive sheet is understandable more for the teachers, and because you are preparing every time in study programs. So it's and it's helping for us the same to have a better understanding of this model. Of course, like Eric presented, we did the interview. We have surveys and interviews together. Of course, we didn't collect a lot of answers, but Remigijus spoke with some outside companies, and we get some responses about that. And our model content, it is PV model systems, which contains fabrication of PV models, series and parallel connections in PV models, PV model parameters, designing grid-connected PV systems, design standalone PV systems, installation on roof and on ground. Location issues. The position of the sun, irradiance on PV model, direct and diffuse irradiance, and components of PV systems, maximum power point tracking, power electronics, batteries, charge controllers, cables. Solar thermal energy, solar thermal basics, solar thermal heating, components of system, ST system and installation, and PVT system, what is quite new. And we have comments from our partners that maybe we need to think or to maybe cancel this description in PV model. And we added circular economy and solar energy. And from the interview report, we got some content suggestions, which we will add to the model, because as I mentioned, it's at this moment only in the pilot model preparation. We will, of course, by all the suggestions, we will correct model which we prepared. And after we will send to all our partners, they will read it one more time. And by corrections, we have to prepare perfect model to use for students. So content suggestions, safety protocols and risk preventions, working with forklift, protection against over temperature and thermal solar energy installation and protection for regular PV energy systems, installation on more surfaces than roof and ground, for example, on water, and the impact of the installation, duration and degradation on PV panels, the importance of the quality of PV panels, DC cables and installation connections, calculation tools, inverter technologies, oversizing, integration batteries with energy management system, application of direct current voltage and smart grids, installation support and structures including ballast plan, writing techniques, direct current, fuse box reinforcement, similar to PV, but more to air conditioning. And because the model is mainly about understanding the concept of system, it might be better to not include, to just broadly mention it. And of course, as we mentioned, that we are the lead partner, so we prepared this model and sent for the colleagues to check it. So we already collect feedbacks from our partners. So during a few months, we will prepare and correct this model to our partners' suggestions. And then one more time, we will send to them to read it, or maybe they will find one more time to change something. So until end of July, we need to have prepare the final version of our model M1. Thank you for your attention.
Okay, just let me see. And arrive until here. Because I'm super nervous, so okay, good morning. Let me introduce myself. My name is Gregorio Blanco. I'm from Valencia in Spain. Maybe you know Spain from Mallorca or Barcelona, but there are more cities, and one of them it's Valencia. No? I'm from a vet school. The name of the school is Chabek. I wear the uniform. And in the project, there are 3 persons involved. From the last week, there is a 4th person, but we have 2 teachers. One is I don't know if telecommunication engineer is a Google translation, you know, telecommunication. And also another one who is architect, and both of them have worked in the companies for a long time ago, and now they are in their school. And this week, when we send the materials to all the teachers to get the feedback, we realized that one teacher who is a PhD, he teaches in uni, he's teaching one subject about eolic energy. So we have discovered one good value in the school. And then me, Gregorio, I study business administration, and I'm like the financial controller of the schools, and I'm also in charge of the Erasmus, of our Erasmus projects, and I am developing some things and coordinating the project. And also we have the support of Panko and Terrendis. We were aggressive, not aggressive, but in our comments. So we are afraid about what happens in the future when we send our material to Panko. For us was quite challenging because the school is focusing on industrial maintenance with its electromechanics, mechatronics, heating and cooling installation. And aeolics was aligned, but not exactly what we teach. So we start some investigations to see what kind of companies and also a lot of technicians. We have think about this structure, no? Some background. It's always fine to see why are we here. Talk about the components of the structure, also description of the system. Farm design or sizing farm design. The picture for my mom, it's impressive. Thank you. And also a return of the investment, because if I work in numbers and I like the idea of investment, but I also like the idea of return of investment. And also I like the idea of circular economy that Jovita present to us, and I have to say that we copied this, and that's because I think it was nice. What have we done? The first thing that we do was contact with the students or former students who are working now in companies. Perhaps you know them. Perhaps you know Fiona, perhaps you know Siemens Gamesa. We have a lot of students, mechatronic students working there. We say, okay, we have a problem, we have a challenge, and we need your help. And then they give us a lot of materials focusing in maintenance. No, we get a lot of maintenance operation and from different companies. We contact also some teachers from other schools in the area of renewable energy. We have studied also the manuals, different subjects in technical study, and also in the uni. Contact with some companies. Obviously, autonomous investigation, and also number 7, the Win Europe. That this website is impressive, and also you have LinkedIn. They upload every day a lot of things, and I think it's super interesting. Some background: at the end, 50% of the electricity demand in the European Union is covered by eolic. The best one is UK, Sweden, Germany. 5th place appears the Netherlands, also France. And Spain is not there, but we will appear later. I think it's like football. Some background, but I think it's not relevant, because if you are interested, you can Google it. But it's something that is not new. They started in 19th century. They realized in 1970s with the oil crisis. The first farm was in 20 years ago, and in the last 20 years, that has grown a lot. And now Spain appears in a better position than before, whereas energy covered by eolics. We were in a meeting last week with Siemens Gamesa, because we as a technical school are really focusing employment, and also Juan Carlos Morón is in charge of the employment agency. And we were in a Siemens Gamesa presentation, and what they were demanding to the vet schools were this kind of profiles: electromechanical mechatronics, renewable energy, and electrical electronics. To do this task, predictive, corrective, lab corrections technicians and commissioning technicians, but also, and I think it's very interesting because it's linked with something that Eric said at the beginning, they are demanding for people who has passion for renewable energy, international context, and also commitment with safety at work. Maybe if you were there, you can understand why safety is important. I'm not going to go deeper here, because we just take all the components, and in our model we describe all the components. That's descriptive, and I think I'm not going to use so much time now to describe. And also we have included a description of the wine system. We have, I think that's super theoretical. We have in the school to focus. We are focusing vet, we are focusing technicians, but we are focused also in high education, level 4, 5, and also 6. So thinking in level 3, 4, 5, we will talk about the maintenance of the wind turbines. That's also a checklist. That's not relevant at all, but part of our model is focusing technicians that need to do the maintenance. And our second focus is engineers. We think about the idea of the wind farm design, the visual impact, how to use the SCADA system, how to monitor online, how to use online tools. So the idea is that we have developed the model in two different with 2 different focus. Digital tools is something that I said in the previous slide. So, and also we have parts for the protection equipment, electrical failing. I mean, all of this. Read by yourself, but you can understand that safety, of course, is something super important. Thinking in the circular economy, that's in the Win Europe. That's in the Win Europe website. This commitment to achieve the full recyclability of our turbines. I think that's an interesting point. I can tell a story, but I can do it later. But the idea is that the circular economy is part of our presentation. The idea that we have for the contents is talk in some theory about reaching description, knowledge about digital tools, knowledge about remote work tools, circular economy, and necessary protective equipment, and a practical part that is maintenance, and it's sizing and designing. I don't know if I disappeared from the screen, sorry. And that's it. No, there's no idea. Perhaps we need that.
You did there or something, or
I don't know what I done. Sorry. Yeah, that was what I said.
Yeah.
Yep. Thank you. Some figures, I mean, they are changing because it says wind energy, how much in Europe electricity, was yesterday. That was from 12. I can promise, under my experience in the plane yesterday, that probably the ratio yesterday was higher than today. Also some, I think that's this Wind Europe website has a lot of interesting figures. And also that's the website I was telling about. I think they have everything. And also you can, guys. And that's my presentation. Please.
Good morning, everybody. My name is Peter van Hout. I'm working at UCLL in Belgium. And we are responsible to build module 3, that's called network management and storage. We're located in Belgium. We have several campuses spread over the northern part of Belgium called Flanders. We have a lot of students, more than 50,000 students, up to a bachelor degree. And we also have a research assignment. And that's why I'm a lecturer and a researcher about renewable energy systems and power electronics. For the content of module 3, there are 3 main topics on it. The first is the energy conversion, where we try to teach the link between the generation, storage, and usage of the energy. Second part is the storage concepts, and the last part is maybe the most important of today is the energy management of all those resources. To get some more in detail for each part of it, first is the energy conversion. We will start at energy production because it's relevant where our energy comes from. And we also want to spend some time at classical production plants, like thermal plants. We know steam turbines, also nuclear plants will be in the module. It's not maybe a good renewable energy source. Should we build more nuclear plants or not? I'm not fond of it. I say, just leave it as it is right now. Don't build anymore and put all your effort in renewable design. But still, we have to mention it because they are there. Also, the combined cycle gas turbines, generating plants with fossil fuels, and combined heat and power, where you have heat generation and also electrical generation. More focus, of course, on the renewable techniques like PV, wind, hydropower system, and also generation of electricity by hydrogen with fuel cells. So very emergent technology right now. It will be a very, very big part in our energy transitions. Also with the energy conversion, when we generate some energy, we have to distribute it. There will be a transmission part. That means on high level, high power, high voltages, the link between the generation plants, the power plants, and eventually at our homes. We talk about energy transport over AC grids as we know it very well right now. With here in Europe, it's 50 hertz grids up to 380 AV. But we also want to mention an upcoming technology, especially for distribution and transmission, is a high voltage DC technology. Because we think that maybe within 10, 20, 30 years, we don't have any AC grids anymore, but it will be all DC grid from the power plants to at your home. Because if you look around, our world is actually DC. It's all DC current, generating current by PV. And the battery storage is all PV. If we start from scratch right now, it will be DC on the grid, not AC. That's a historical reason from Tesla and Edison more than 100 years ago. Then we have to take into account there will be a lot of conversion of this electrical energy and the voltage levels, high voltage to medium and low voltage. We do that with AC transformers, as a well-known technology. For the DC conversion, it will be DC-DC conversions, and it's thanks to power electronics. We can do that as today on a very efficient way, and that's why we think the future grids will be DC. Today there are already a lot of high voltage DC line, especially on the north of Europe. 2 years ago there was a NEMO link between Belgium and UK, 1 gigawatt transmission line of H voltage DC with all of benefits. And then last part of it is discussing the voltage levels. What will it be for transmission, or what will it be the DC at your home? Here in the Netherlands, a lot of commissions are involved of thinking about it. They have quite a pioneer role in it. What will the distribution be in your home? It's 24 volts, or 300 volts, 350 volts. You know, not for sure yet. And also protection of the grid and the transmission distribution is important. The second part, we are going to discuss the energy storage concepts. There are a lot of concepts already known as today, mature technologies and very new technologies. Today, electrical storage most of the time will be in batteries and lithium ion, more specific, because when the rising with the cell phones, there was a lot of technology growth in the lithium ion technology, but now is a really mature technology. But there are also other batteries in the field, like salt batteries or flow batteries, maybe for other appliances. And also take into account the batteries which are today in our electrical vehicle. And we can use all the electrical vehicle as a very big storage capacity. And that's called vehicle to G, but maybe another term is vehicle to X, vehicle to everything. Another storage concept, water by pumped hydro, also very mature technology, which can provide you with a lot of power, maybe the same power as a nuclear plant. It's very helpful in our energy transition. Other techniques, maybe not known that well, mechanical storage by flywheels or compressed air, where we're going to store some air with a pressure beneath the surface. And heat also very important, like geothermal storage in the ground will be added at the module, and heat networks will also be mentioned. Electrical, we do electrical storage by battery with some kind of chemicals, but I believe that the molecules may be even more important to do electrical storage, not directly conversion to electricity, but store them in molecules like H2, hydrogen, methane, ammonia. They will be big carriers and storage of energy, not only for electricity, but also for building and industrial plants as a building block. Also, CCS, if we go to our climate change, the most important reason of the climate change is too much carbon in our atmosphere. And there are several techniques to store the carbon. We call that CCS, carbon capture and storage, and also carbon capture and usage. So we capture the carbon out of the air and use it to build other synthetic materials. Another new technique I heard a few months of is store hydrogen in ice. They call it, you just can have a big capacity of hydrogen just stored in your refrigerator. It's a technique with clatrates. It's quite a chemical and not that difficult, but it's a very promising new technique because you can store hydrogen under low pressure. If we now store hydrogen, we need up to 700 bars. It's very high pressure. Last part is the energy management of all those power and electricity. Also involved in the module. First of all, we take into account some grids, the power grid, smart grid, microgrid. What's the difference between them all? For sure, it must be smart. You must be use the energy, generate and use on a smart way. Some techniques that you can use is a DSM, a designed demand side management, not just that if you need some energy, let the energy plant do the work. No, just use the available energy that there is. You must manage your own time and capacity. SCADA systems also very important to monitoring all the energy flows on our big screens. That's what the PSOs are doing it. The system operations, they are controlling all the flows with SCADA systems. Then virtual power plants is also upcoming. That's something like if you have a lot of local energy generation, maybe in the neighborhood battery storage, maybe in the neighborhood hydro pump system, you can collect them all in a virtual power plant that will act as just one generation plant. It's more like a service that can be offered. Also, local energy communities will rise because the ancient way of production of energy was central in the middle of a country, a big power plant, and distributed to abroad all of our country. But now there will be a lot of decentralized production systems, and maybe better in one small urban area. You have a local energy community where everybody helps with your PV installation at home, or maybe battery storage for a few megawatt hours somewhere in the street, and they can act as local energy communities. To make everything smart, it's very wise to measure everything and do that on a smart way. I think everybody in Europe is gonna get a smart meter. That means that we can collect all data of your consumption and maybe your injection of the energy, not for residential use, but also for small enterprises. and so on. We also spend some time at home appliances, how to deal with the energy that you have, and maybe if you have a little storage at your home, you can use energy anytime you want. If you don't, maybe you have to schedule it for yourself, do the dishes on a moment if there's a lot of energy. Not only a lot of energy, but maybe better is when the price of the energy is low. And that's the last point. The point is the pricing of the energy. As today, our bill is most of the time how many energy you take, how many kilowatt hours you get a bill in euros. But the future will be that the bill will be built on how much capacity you need. And more important is how many kilowatts do you use at your home, just to make sure that we don't have to put very big cables into the soil, because that's very expensive. It's better to spread your load and do it with the grid we already have. I think that will be more important than billing by energy consumption itself. That's it for me. That was my contribution. If there are any questions, you can send them now. No, if not, then we'll be the next speaker. Yeah. Yeah.
Second thing, sorry for this.
Okay.
So, hello everybody, I'm Philippe from Renewable. So I'm a teacher at Technological Institute, and so it's part of my job, and I'm also a researcher in fundamental physics with application to a new kind of renewable energy, which is called osmotic energy. So it has not been presented yet. It's something that started to be considered I would say 10 years ago, and that's becoming stronger and stronger now. The potential all over the world is larger than the actual electricity consumption. So it's really something that should grow in the coming years. And yeah, in France, there is a plant that will be installed on the Rhône, on the meeting point between the river and the Mediterranean Sea. So yeah, I'm sure that in future Erasmus Plus project dedicated to renewable energies, this blue energy or osmotic energy will be part of a future project. So I will focus now on this hydrogen module dedicating to green production. It's a module that I will build in collaboration with Tenerdis, Philippe Cluzel from Tenerdis. This module is divided in 7 parts, maybe 7 nodes, because I like very much this idea of nodes. So these different chapters are actually independent quite independent one from another. There will be a first part dedicating to a brief overview of hydrogen, its properties, as I will detail later, and also discovery and current usage. Then a second chapter dedicated to the need of a green production from water electrolysis. And this second chapter will be more theoretical, while the three next chapters are more technological. So first, water treatment chapter to prepare water for electrolysis, which will be the fourth chapter. Then H2 storage, different strategies. Chapter dedicated to life cycle considerations. And finally, safety rules. That will be a summary of rules introduced in the previous chapter for each part of the system for hydrogen production. So hydrogen, the word has been introduced by Lavoisier as the generation of water. It's incolor gas. So here I put a picture with purple glow, which is the plasma state of hydrogen. And what is important here is to see that current preparation of hydrogen is mostly based on fossil fuel. And the hope is to be able to completely change this current state using rather renewable to produce hydrogen from electrolysis. There is a major usage of hydrogen to produce ammonia right now. And the idea of the next model will be to present a new usage of hydrogen and of energy to rescale, I would say, this current usage of hydrogen. So hydrogen will be a way to store energy and to develop a new usage. So this second chapter dedicated to the building of hydrogen, the generation of hydrogen from water, will introduce theoretical basis. It will be divided in three parts. The first part dedicated to osmosis and reverse osmosis that is needed to purify water before usage within electrolyzers. So this first step will require thermodynamics and transport in porous media to be understood. Then we will go to electrolysis with electrochemistry basis and kinetics limitation during the process. And then we will continue on the different way, I would say the more advanced way to store hydrogen, either as a compressed gas or based on liquefaction or adsorption strategy with the different theoretical tools related to these three types of storage. So this whole chapter will be more of level 6 or 7 engineering level, and it will be independent of the next chapter that are more technologically oriented. So this first chapter, this first technological chapter, which is chapter 3, is dedicated to water treatment. You can't use water additives. It needs to be purified before using it in an electrolyzer. So there are 3 steps. A first pre-treatment stage based on removal of suspended solids, so filtration, and also to remove biological elements. Then there is a reverse osmosis, which is the main step based on porous fiber with tiny holes, nanometric holes, with different type of membrane, and if needed, ultra high purification, which will be the last part of this this model. Then we will go to the fourth fourth chapter dedicated to electrolysis to produce hydrogen. So here again, we will focus on three main technologies. First technology, which uses steam, water under a steam state, with a different kind of approach based on steam, either solid oxide production, or proton exchange membrane production, or molten carbon system. Then we will focus on proton exchange membrane, which is probably the most promising strategy because, as shown on this on the graph below in blue, this strategy is able to sustain large current density. And last, the alkaline strategy that is maybe older but still in application. So yeah, we will describe the different constraints and maintenance required for this different strategy, and also go into details about the different elements which are present within an electrolyzer. So here there is the picture of the proton exchange membrane strategy to produce hydrogen. The storage chapter will describe the different way to store H2. So we will spend most of the time on compressed gas with different compression strategy, as shown on the right-hand side. So compressed gas, as has been said, has been said, required to reach high pressure to have to reach an energy density large enough for many applications. So beyond compressed gas strategy, cryogenic storage in a liquid state is also considered, maybe for planes. But this strategy requires a lot of energy to reach a liquid state. So it's a drawback of this second strategy. There are other strategies. So adsorption or absorption within a solid system, and also storage within other liquids, like ammonia, which is already produced at a large scale, methanol, formic acid, for instance, and also hydrates, as mentioned by Peter. So hydrates or clatrates is a promising strategy, except that the formation of this hydrate or clatrate is not so easy. So it's something that will maybe grow, but is not the direct system that will be used at least at the technician level. It's more in progress. And you can see here on the graph the different level of storage in terms of mass or volume. So from a technological point of view, I would say that compressed gas is still the most promising way for large-scale development for hydrogen storage. There will be a chapter dedicated to life cycle consideration. So here you can't read everything, but what I want to emphasize is the fact that, for example, for proton exchange membrane electrolyzer, actually, what is really important is what we call base of plant, which is all the auxiliary system required for the system to work. And in terms of impact, actually, these auxiliary systems are quite important, and it's needed to take them into account. And based on this, we can find a new strategy. For example, here in the hotel, we have a card to access the rooms that are in wood rather than plastic. So at every level, we can
somehow flip to new strategy, but analysis is needed before to make such a change. So within this formation, it's important that the technician or engineer have in mind what can be changed actually. To finish, we will have a safety rule summary considering electrical hazard, high pressure hazard, cryogenic hazard, and fire and explosion, which is probably the most obvious. For instance, the fire of hydrogen is not visible, except if you have an infrared camera. So it's something which is particularly specific and not obvious and dangerous. So I will move now. Oh, yes, I forgot. So just a bit overview of the organization. So we plan 12 hours of practical divided in 3 parts, a part on water filtration, then H2 production and gas compression. We already have these practical ready in Grenoble, and then lecture plus exercises in a block that will be approximately 10 hours with the different concept I already mentioned. Here I list the competencies that need to be reached at the end of this module. I move now to the usage. So the last module, how to use, how will we use energy in the future energy mix. So I think it's quite difficult to dissociate usage from the energy mix, and this module will be produced in collaboration with the other member of the team. I plan 5 chapters. First chapter, introduction, presenting the final usage in the global value chain. Then to be able to use the energy, there will be a need of electricity or heat production from gas. So we will focus on this cogeneration step. Then we will show different examples of transition where we will move from, for instance, from existing strategy to a new strategy of usage of energy. A chapter then concerning opportunities and constraints, because actually it seems better to go to renewable, for instance, but it's not necessarily easier. So there are constraints. And finally, exploitation and maintenance with case studies to cover all the change from production to usage of energy. So concerning the final usage, actually a major change with respect to what we have right now is the fact that there will be interconnection between 2 networks that are quite separated right now. We have an electrical network and we have a gas network, but the interconnection is quite limited. With the hydrogen and maybe production of biogas, hydrogen being considered as a way to store energy, we will have an interconnection between these 2 networks, and the usage will definitely be linked to this interconnection. So there are arrows showing the different flow of energy within the different networks. There are losses during the different transformations. So this is also something important that will be presented in this chapter, the energy which is really usable at the end of the chain. Here I show 2 illustrations, for example, for transport or stationary, which is things that will be described further in the following chapter. So concerning once the energy has been stored, for example, under a gas state, there is a need to recover the energy, and the most efficient way to recover is to make cogeneration, because it's really difficult to produce electricity only. Heat will be produced at the same time, so it's necessary to use the heat that will be produced. And there are 2 main strategies: either using, I would say, classical system, gas turbine and heat engine. Complexity will emerge from the fact that hydrogen can be used as a way to power this system. And we will focus also on fuel cell, which is a new strategy to recover electricity, which is somehow similar to proton exchange membrane electrolyzers. So fuel cell will be probably used at a lower scale with lower power. And also, we will focus on the efficiency of this different system. Gas turbine may seem quite old-fashioned, but in terms of efficiency, it's not so bad with respect to fuel cells. So it will definitely continue to exist with the ability to use a mixture of gas, which is not necessarily possible with fuel cell. Then a chapter dedicated to example of transition. So maybe the domain which is the most obvious is transport. We will move from heat engine to probably electrical power sources, or maybe hydrogen transport, probably for high load like train or trucks. And for sure, we will need a transition. Use the changes that will emerge from such a transition, and similarly, in the way we will use energy and also produce energy, there will be changes in residential and industry. Currently, we have local production of energy at the individual house level. We may have a PV and other systems that will emerge that will also be linked to the usage approach. So opportunities and constraints in the future energy mix. So I will focus here in this model on the coupling between hydrogen and methane, which is not so trivial. We can imagine complex strategies where we can recover hydrogen from methane. We can imagine to produce methane, combining CO2 from industry with hydrogen, and all these can contribute to new usage. Peter mentioned carbon production for byproducts. It's also a strategy that is based on this mixing. So this CH4H2 coupling is very promising. This decarbonated electricity supply and usage has strengths but also weaknesses. So strength for sure is lower production of carbon dioxide, but weaknesses rely on the fact that most of the sources are intermittent and diluted. I speak about wind and photovoltaics. So you have a need to store. It's what we describe, but there is also a need to have a peak power that is much larger than the average power. And this is something to have in mind, because you will need to develop a lot of wind turbine. And for solar, this is the same thing. Unfortunately, the sun is not there during the night. So all this to say that there is a need, as it has already been said, of a global decrease of energy consumption if we want to rely only on renewable for all our applications. This allow me to move to the last chapter. So we see here that we need also some adjustment within the team. The goal here with this chapter, I wanted to give an overview of the usage of energy, but not only, to show all the bricks required up to the usage, emphasizes the job related to all these bricks in terms of exploitation and maintenance. So here on the picture, I picked this picture to show also the safety, the importance of safety. Here on the picture, the guy does not wear an helmet. So this is typically on the left-hand side on the wind turbine. This is typically something that should not occur. So the goal here is to emphasize all the constraint imposed by maintenance, and also to demonstrate why maintenance can be an attractive job. Working up in turbine can be attractive for many young people, so it's also a way to attract people to this job. So this is for electricity production. You can have similar things for solar and so on. Then what is more related to this usage module will be the production, for instance, of hydrogen. And then, so this is for the storage part, and then usage, where here I pick a picture concerning maintenance of a turbine. But for fuel cell, you have exactly similar things with replacement of membrane within the fuel cell. So all the timing of replacement, all the scheduling of pieces to be checked and everything to be controlled will be part of this chapter, which will be based on 8 hours of practical. So a first practical dedicated to the discovery of the global chain from photovoltaics to usage of electricity based comprising electrolysis for production of hydrogen, and then recovery with fuel cell, and another practical which concern more the gas and water handling within a fuel cell for electricity and heat cogeneration. And then again, like the previous model, 10-hour lectures plus exercises to have a global view of usage in combination with the energy mix. And I thank you for your attention. So the idea is to develop this module during the 2 coming years. I would say that the first module should be ready by the end of the second semester in the academic year, as Jovita said. So this is for the first module, and we will progressively test this module and in the same time develop the M2, M3, and so on.
Is it also for all models is the same planning, or started the second semester? Pretty much. The entire project will last for 2 more years. So in December 24 is the end of the project, but that includes testing. So part of it will be ready before. But at the end of 24. So 10 hours lecture and some practicals. Are the other modules also 10 hours lectures? Are they the same?
Maybe we can say the question again.
Yeah, so the question is the structure of the different modules. Here I introduced for this last module reportation in terms of half practical, half lectures. Yes. And the idea is to have a similar decomposition for the different modules with some adjustment, but yes.
To what extent are you operating in the industry on this? Because companies like Air Products and LET they have decades experience with hydrogen, gray hydrogen, but in terms of transportation, storage, safety aspects, they're as well developed. Are you using that information?
Yes, I mean, in at least in France, we have this campus des métiers et des qualifications. So I need to make a translation, probably campus for jobs and qualifications, which is really focused on this idea of interconnection between academics and industry, in particular Air Liquide. So the idea is really to take benefit of their knowledge, to really build this model with things that are really industrial, if you want, and also to promote the implication of the industrial within such a formation, because it's also important for them to have future technicians and engineers that are trained.
If I can
Sure.
complete, there is also don't escape. There is also in the partners we have also Tenerdis, which is a cluster and a competition cluster whose job is to make the link with the companies and to take their comments and advice. And so yes, this part is taken in account. And Cyril didn't say, but I think it's the same for the other universities. But the IUT works also with different companies.
And it's, we still have about 40 minutes left for this room. So I invite everyone, if you want to stay, take another cup of coffee and we can discuss more at the tables or just standing here. And we close the section.
Maybe
also
can,
for the viewers online.
Maybe we can ask if the
attendees online have questions.
That's right.
Are there any questions?